All right. Good afternoon, everyone. Let's start. Let's start. So first of all, we have released the homework one, which are just practice of our learn, probability distributions and their properties, and also including conjugate prior exponential family, which we're going to talk about today. So again, I mean, the time should be more than enough. We have 18 days, so 16 days. No, 18 days. So, but again, if you have any question or you want to seek for help, please do not hesitate and come to the office hour or ping us on the canvas. Don't hurry. I mean, at the last day or 3 hours before deadline, that won't be sufficient. But if you just take a closer look and starting, say, this Thursday or Friday and trying to work out every problem, so you will feel much more relaxed and at least than homework 0. Okay, so let us, oh, by the way, also please consider your project choice and make a very short description about project choice, the team member, and also the tentative 3 papers if you want to do the paper rating. Again, that list is not the final list. You can change the paper you want to read at any time, as long as you have enough time to go through it. But we just need your preference to the project. Okay, so yeah, let us continue with the probability distributions. In the last lecture, we talked about, in addition to some beta distribution and categorical, no, Bernoulli distribution, categorical distributions, which describe discrete random variables, right? We talk about how to assign a prior over the parameters of those distributions. Like for Bernoulli distribution, we know that parameter is some probability, right? Like you toss a coin, you want to know the chance that you see the coin has the head up, right? That chance we denote by P is the probability between 0 and 1, right? If we want to further assign a distribution over that probability, a commonly chosen prior distribution is called beta distribution, right? And it will generate, if you use that beta distribution to generate a random variable, it will give you a number between 0 and 1, right? And just don't get confused. The beta distribution is a continuous distribution because it models the probability itself between 0 and 1. It's just restricted to the range between 0 and 1, right? And then we can extend the case to the categorical variables, right? Suppose your random variable has k possible outputs, right? So know that that random variable can be modeled by some categorical distribution. That distribution is parameterized by a probability vector, right? Suppose you have 3 possible categories, right? So you know to generate such kind of category, it is controlled by some 3-dimensional probability vector, like 0.1, 0.3, 0.6, right? Then the next question is that, what if I want to assign a probability distribution over the probability vector? That leads to the so-called Dirichlet distribution, right? So you can view that as a kind of general, natural extension of the beta distribution, right? And then, then we talk about the continuous distribution, like a Gaussian distribution, right? A Gaussian distribution, everyone should be familiar with that, right? And we need to know the multivariate version of Gaussian distribution, right? So how do you use the completing the square trick to derive the conditional Gaussian distribution, to derive the marginal Gaussian distribution? Although those results kind of like classical, you don't need to prove it in practice, but those completing the square trick is very, very useful in doing any probabilistic modeling. Right? And then we'll talk about like, what if I want to assign some prior distribution over the parameters for Gaussian, right? So for mu, the mean of the Gaussian distribution is pretty straightforward. You can assign now Gaussian, but how about the variance, right? So first talk about if we instead want to assign a distribution over the inverse of the variance, which we call the precision. a common used one is called a gamma distribution. And the gamma distribution guarantees that you're going to generate a random variable to be positive. Right? And someone asked, what is the, if I do this integral, the integral must be in the positive region. It is, or in other words, you can view the definition of this gamma distribution density is that, okay, for all non-positive choice of lambda, its density is simply 0. Right? And again, the gamma distribution is parameterized by two parameters, skew and rate parameter, A and B. They have some nice properties, and you just need to know they have how to compute the expectation variance and the expectation logarithm. They're all kind of formulas. You don't need to know how to derive that. Just leverage the results, right? And and also we know that the kind of like counterpart to the gamma distribution is the inverse gamma distribution. Right? If some random variable follows gamma distribution, then its inverse follows the so-called inverse gamma distribution. Right? So the reason of introducing inverse gamma distribution is that what if we want to assign a prior distribution directly over the variance rather than inverse variance? Then we can assign inverse gamma distribution. And later we'll see gamma distribution is conjugate to the Gaussian distribution. And if you parameterize Gaussian distribution with this precision parameter, and if you want to parameterize your Gaussian distribution with variance parameter directly, then inverse gamma distribution is a conjugate part. Yeah, inverse gamma distribution is just saying, okay, I want to say the motivation, right? So when we talk about gamma distribution, right? So we're talking about how do we assign a prior distribution over inverse covariance. So 1 over sigma squared. Right? Some people feel, okay, this is not very natural, right? What if I want to directly assign the prior over sigma squared, right? Rather than its inverse? Then what's your choice? A better choice will be inverse gamma distribution. And the inverse gamma distribution will enjoy the same computational convenience as the gamma distribution. We'll see it later because it is they're both conjugate to the Gaussian distribution. And we'll explain what is conjugate, what is conjugate prior. And then we can extend this case to a multivariate Gaussian distribution where now our variance becomes a covariance matrix, right? And the natural problem will be, okay, what if I want to assign a prior over the covariance matrix or inverse of a covariance matrix? Again, following the same lead, right? We first look at the precision matrix, which is the inverse of covariance matrix. If we want to assign a prior over the precision matrix, a natural choice is so-called Vcharge distribution. Right? So you can feel like Vcharge distribution is some guy who can give you a positive definite matrix, which is kind of a sample, right? And it's parameterized by a positive definite matrix, which is called skew matrix, and the degree of freedom, and similar to the gamma distribution case, right? If this big lambda, this is a matrix, it follows the gamma distribution. That means its inverse follows the so-called inverse Vcharge distribution, right? And the parameter here is almost the same as that, except that in the inverse Vcharge, you have to take the inverse of the skew matrix. So again, the motivation of this is that it's similar to the scalar Gaussian case. What if I want to assign a prior directly over the covariance matrix rather than its inverse? Then I can choose to use a inverse Vcharge distribution. Okay, so this is a quick review of what we have seen so far. So the last commonly used and important distribution is called student T distribution. So what is student T distribution? So you can view it as an infinite mixture of Gaussian distribution. How can we see this, right? Suppose we have a Gaussian random variable, right, x, which parameterized by the mean parameter mu and some precision parameter, right? Remember, precision is the inverse of the variance, right? And now, if I want to assign a prior over this precision tau, right? C, just with gamma distribution. So this gamma distribution, as we have saying, parameterized by A and B. So what if I want to know what is the marginal distribution of X? To get a marginal distribution, well, you have to integrate out the inverse variance tau, right? So if you do this, right, if you want to integrate, if you integrate out the precision tau in terms of this gamma prior, it will give you a student t distribution. Okay? So you can try to do that, but it's not required. It's kind of quite tedious. It's kind of examining your calculus capability, but basically you can do kind of repeated integral by parts. It's quite tedious, but then you can get a form in this way. And then you can further simplify it by, remember, because this integral now is determined by the natural, the parameter of gamma distribution A and B, right? And also this, this mu, right? So if you can reparameterize them by define a new set of parameters like nu equals to 2 times A, lambda equals to A over B, right? So then substitute them for the A and B in your naive result, you got this final form. Right? This is the common form of the student t distribution. You can say from Wikipedia or your textbook. Right? So we call mu as mean, which is the same as the Gaussian distribution. Right? We call lambda, which is A over B, as precision. Okay? And nu here is a degree of freedom. Okay? So why do we call lambda as precision? You can see that this is still a quadratic term here, x minus mu to the square, right? And lambda here is multiplied. It's kind of similar to the Gaussian case where if you use precision, well, it will multiply with the square term, right? So that's why it is called precision. I have a degree of freedom, right? And of course, we need to ensure that the degree of freedom is bigger than 0 to have a valid student t distribution. Again, how to derive this part is not required. The important thing is that how do you understand how the student t distribution comes from? You can view as, okay, what if I don't know some Gaussian random variable? I don't know the variance or precision for some Gaussian random variables. I want to integrate all possibilities across to according to some gamma prior. That's where you get the student t distribution. But again, the calculation procedure is not very important. You just need to know, okay, when I need to look up the form of student t distribution, just find the right place to find it. That will be enough. Mm-hmm. No, it's not, because you have to assign another prior over mu, right? Then you have to integrate on mu simultaneously. That's not necessary to give you the same distribution here. But if it is, but it shouldn't be the student t again. But this need to be double checked. This need to be double checked. Okay. So now from this integral, we can see where the infinite weighted sum of Gaussian comes from, right? So again, we will like the integral in general sense is kind of summation, right? And we will like, okay, this integral is kind of varying x from 0 to infinity, right? There are numerical, there are numerous choices of x, right? For each choice of x, you have a weight comes from this gamma density, right? So you just sum them up, right? That's where you can will the whole student t distribution comes from an infinite weighted sum of Gaussians. That's why people also call student t distribution as an infinite mixture of Gaussian distribution. Right? And later we'll see that Gaussian mixture or finite Gaussian mixture is kind of very, very popular and powerful models. Okay. Any question regarding the idea of student t distribution? Okay. So what's the qualitative difference between student t and Gaussian, right? So student t is known to have a heavy tail in its density. So basically, you can see that these different curves correspond to different choice of the degree of freedom nu, right? So when the nu goes to infinity, it returns to a Gaussian distribution with lambda as a precision. But when nu is not infinity, right? Nu is just some finite positive number. You can see that the density, when it is far away from zero or from its mean, is larger than the standard Gaussian. That's why it's called heavy tail. For the standard Gaussian, you can see that, okay, the density, the probability density or mass, kind of like more concentrated surrounding the mean, right? Here, mu is taken as 0. But when your random variable takes values far away from 0, the density decays very fast. Okay. You can see that here and here, decays very fast and approaching 0 very fast. But for student t in general, you can see that it also put large probability mass surrounding the mean. But when you get distant from the mean, the density decays, but not that fast as the Gaussian distribution. So that's why it's called heavy tail. But what's the benefit of heavy tail? In statistic research, right, heavy tail distribution is often more favored than those light tail distribution. Why? Because heavy tail distribution is more likely to resist the noise. So here's one example. Of course, is a copied figure from the PRML book. So we'll point the chapter for your reference, right? So if you take a look at a set of data points here, right? So here, for convenience, we just show the histogram, right? So now you can see that this set of data points kind of like less noisy, is a good set of good data points. If you use student t distribution or use Gaussian distribution to fit them, in other words, we can assume them follow some Gaussian distribution and then perform MLE, maximal likelihood estimation, right? So you get this red curve, right? It's a fitting, right? After some MLE estimation, you get your Gaussian distribution. It's pretty reasonable, right? So you can also assume this set of data points are coming from some student t distribution, and then you conduct MLE, and it'll give you a green curve. And you didn't see green curve. Why? Because it overlaps with the red curve. So you can see that when the data points are distributed very in an ideal way, it is not weird. It's kind of like a single, concentrated in a single mode. I mean, using student t or Gaussian standard or Gaussian distribution to fit data seems to have nothing difference, right? Now, if we switch to the second figure, suppose we have some fluctuation, some kind of unexpected noises, right, showing up here. What will happen, right? If you still use Gaussian to fit this data, meaning that, okay, I'm gonna throw this set of data points, including these noisy data points, and then perform MLE to fit the Gaussian, then this green curve is your Gaussian. It's not very favorable because I don't want some kind of little noises to largely change my fitting, right? In other words, the Gaussian distribution is very sensitive to the noise. Like if you have any kind of noisy observations far away from other data points, your Gaussian is very easily to be flattened. But if you use student t to estimate the distribution, right, and you use MLE again, you still observe a kind of very similar density as in this case. That's the power of the heavy tail distributions, because they're much less sensitive to noises. And the underlying reason is that, okay, because they can assign a relatively larger density for the points which are far away from the mean. So even you use MLE, it's okay, right? But for Gaussian, because it kind of like assign a very small density over the distance very far away. So you want to fit them, you have to move your mean and change your variance to make this likelihood to be large as well. Okay. Any question? Okay. So now, again, we want to extend student t distribution to the multivariable case. So we have a multivariate Gaussian distribution. That means we also have a multivariate student t distribution, which is rarely seen in many statistical book. Right? But here we want to give some reference because it is important for some branch of probabilistic learning, right? So as we mentioned before, right, student t distribution can be viewed as some integral of the Gaussian distribution and some gamma prior, right? So it actually has another form where we can reparameterize the Gaussian distribution's precision by two parameters. One is lambda, one is eta. And eta here, we assign another gamma distribution, but lambda here is fixed. I mean, this parameterization is mathematically is the same as what we have shown just a moment ago. It's just another mathematical transformation where we define this nu to be 2a, lambda to be a over b, which is same as student t's distribution, right? And eta now is defined as tau times b over a. So it's just some kind of variable transformation, right? And what's the benefit of this variable transformation? We want to use this to extend to the multivariate student t case. How? Right? We still assume, okay, this eta is a scalar, follows a gamma distribution. But now we're going to change the lambda here to be a matrix. You can visualize, okay, it can be some precision matrix for a multivariate Gaussian distribution, right? And then we multiply this precision matrix by some eta, some coefficient eta, which is scalar. Then we'll assign eta a gamma prior distribution. Then we want to integrate out this eta and see what is going on. If you do this integral, it will give you the multivariate version of the student t distribution. So now you can see that the multivariate student t distribution is parameterized again by the mean parameter mu and precision matrix lambda, and again degree of freedom nu. And the form is pretty similar to the single variable case, right? Except that you're gonna, this, because this is a precision, now you have to put it as a quadratic form, right? And here you have to change it to a determinant of the precision matrix. Again, how to calculate this to derive this form, how to arrange to this form is not required, but just to give you a sense, how in what kind of idea we can extend the single variate student t distribution to multivariate student t distribution. It's just based on some kind of transformation, right? You kind of decompose your inverse your precision in a multivariate Gaussian distribution by a precision matrix and by a scalar you apply. Then you assign a scalar a gamma prior. You do the integral. You end up with this. Right? So here are a few properties of the multivariate student t distribution. Like mean is mu, and the covariance is not simply inverse of the precision. It's actually you have to multiply a factor, which is nu over minus 2. So that means if you want to have a valid covariance matrix, you must have your degree of freedom bigger than 2. And also the mode, the maximum at which your density takes the maximum value is mu. And also we have the conditional distribution for multivariate student t distribution. I want to we won't list in our lecture, but if you're interested, you can take a look at these two literatures. They can show you how to what is the form of conditional multivariate student t distribution. So why do we introduce this? Because there's one very important branch in probabilistic learning. It's called Bayes optimization. Like if you want to optimize something, right? You want to optimize some function. You want to find its maximum or find its minimum. But unfortunately, you don't know the function form. You don't know if it is a quadratic function plus sine or cosine. You don't know the form of it at all. What you can do is just every time give an input and query at the function value. But then can you tell me what is the maximum of function value? This is a very widely used, like if you want to tune the hyperparameter for the neural networks, if you want to optimize some layout of the materials in some design problems, or you want to design some chemical materials so that their potential satisfies some constraint, is very important. And the popular techniques of solving this is using the so-called Bayesian optimization. And the key idea is that, okay, I'm gonna build up some probabilistic model to approximate a function. One such model is called the Gaussian process. Well, it links to the multivariate Gaussian distribution. And you can imagine that you can continuously query new function values and throw them into your Gaussian process model. So your Gaussian process model is kind of get closer and closer to the ground truth function. At the same time, it can point you at which point to query at. Then you can get to know where the maximum or optimum of the function value is. As we just mentioned, right? Gaussian process is dependent on the multivariate Gaussian distribution. And the Gaussian distribution is sensitive to noises, right? So a natural improvement or natural revision of the Gaussian process is called student t process, because its final version, which is called multivariate student t distribution, is much less sensitive to the noises. So there's a bunch of research showing that, okay, like in computational physics or simulation applications, it shows that student t distributions performs better than Gaussian process in optimizing some unknown black box functions. Okay, but just give you a sense why we would like to introduce this. So, okay, so now we have introduced the commonly used probability distributions, which we're gonna use them to introduce our probabilistic models throughout this semester. What you need to know is that what are the commonly used distributions for binary, categorical, continuous random variables, and for multivariate Gaussian distributions, know how to derive the conditional distribution and marginal distribution, and the commonly used prior distribution of the distribution parameters, like a gamma for the precision in Gaussian, beta, and eventually for the probability parameters, right? For discrete random variables, and also know how the student t distribution is derived and why its heavy tail property is good. Okay, so now we're gonna switch to another important topic. It's called conjugate prior and exponential family. Okay? So so we're gonna first talk about Bayes' rule, and then we will give a definition of conjugate prior and why people are looking for conjugate prior. And then we'll give some common used examples. Then we'll talk about a very important concept. It's called exponential family. As the name suggested, it's just a family of distributions, but it takes the key role in the probabilistic learning and the inference. And we'll talk about the general form of the conjugate prior for the exponential family. Okay. So, oh, by the way, I want to emphasize one point. So you might see quite a few like derivations and mathematical formulas in our slides. Due to time limit, we won't be able to show you, do the hands-on derivation of every detail. But those slides have a clear list all the steps. So we strongly request everyone after class follow those steps to manually check those results. After only doing that, you will have a good impression, understanding of that. Oh, sorry. I don't know why it comes here. Oops. It's annoying, right? Let me first show. Okay, here we go. I need to change the pointer again. Okay. Yeah, we have reviewed MLE and MAP principle, right, which give our point estimation of parameters. But we have mentioned that this is not what we want, right? So we actually, that's bad. Why this guy? Sorry, I need to hide this bars. It's really annoying. Okay. But we mentioned that this is not ideal, right? Ideally, you want a posterior distribution of the parameters given data rather than just giving points, right? So, however, according to the Bayes rule, right, if you want to compute the posterior distribution, we have to divide the joint distribution by the marginal distribution, right? So the joint distribution is usually specified by your probabilistic model, right? You define the prior of the parameters, and given the prior, how do you generate data? But for the marginal distribution, you have to marginalize out all the random variable, right? This is really hard. And this integral actually is the key bottleneck of the probabilistic learning. Or in other words, the central challenge for probabilistic learning is to calculate this marginal distribution of the observation, right? So in most cases, the posterior distribution cannot be computed following Bayes' rule due to the intractable integration, right? So then before we come to like other more general strategies like Markov chain, Monte Carlo sampling, variational approximations, right? People have thought about, can we kind of like narrow the range of our problems? Like, can we find a set of distributions such that when we compute the posterior distribution, we don't need to worry about the intractability of the interval, right? We can directly give you the posterior form. One such set of distribution is called conjugate prior. So we introduce a special case where we can compute the posterior distribution analytically, right? So what's the definition of the conjugate prior, right? So suppose we are given a prior distribution and a likelihood function, right? If the corresponding posterior distribution has the same function form as the prior, then we call this prior distribution is conjugate to the likelihood. That's the definition of conjugate prior. Basically means, okay, if I use prior A and then multiply with likelihood B, and then I can show that the posterior distribution will follow the same form as prior A. We only change the parameters. Then we say the prior A is conjugate to the likelihood B. That's it. Okay. To give you an example, right? Beta prior distribution is conjugate to the Bernoulli likelihood. How can we see that? Right? So we know that the prior distribution over this mu, remember mu is the probability, the chance that you have your quorum has up, right? So it's a beta distribution is proportional to mu to the power of a minus 1 minus mu to the power of b minus 1, right? So now let us look at the likelihood, right? So given mu, you suppose you observe x, right? X is either 1 or 0. So the likelihood, which is mu to the power of x, 1 minus mu to the 1 power of 1 minus x, which is a Bernoulli likelihood, a Bernoulli distribution, right? So now if we multiply them together and I want to look at the posterior distribution of mu, right? See what we can get, right? If we multiply them together, you see that we can directly merge the power, right? So it's mu to the power of a plus x minus 1, right? This guy plus this guy. And 1 minus mu to the power of b plus 1 minus x minus 1, okay? So this form tells us the posterior distribution is a beta distribution, okay? You even don't need to calculate the posterior form. Don't need to calculate the normalization constant because the all terms regarding mu has the same form as the beta prior, right? So that means the posterior is another beta distribution, except that now we need to change the parameters, right? The parameters now becomes a plus x and b plus 1 minus x. That's it, right? And it's very natural because you have a prior, right? You integrate some likelihood from data. Of course, you need to change some parameters, showing that you have integrate information from data, right? So this tells us the beta prior is conjugate to the Bernoulli likelihood. Why? Because the posterior follows the same form as the prior, except that the parameters are changed. It's not necessary. It's not necessary. Yeah. I know what you're saying. I mean, in most of the cases, the likelihood has a different form as from the prior. You can see the likelihood here is a distribution for x. It's not for mu. And although when you multiply them together, because right now you want to obtain the distribution over mu, right? Posterior distribution over mu, you see that, okay, they kind of like end up with the same form as the prior. But in most of the cases, you will see that the likelihood doesn't have the same form as the prior. And here again, I mean, please be aware x is either 1 or 0 because x is the Bernoulli experiments of outcome, right? So to give a more intuitive example, right? So suppose this is your beta prior, right? Your prior parameters 2 and 2. So this density, this red curve shows the prior density, right? And now you have observed the value x is 1. So remember, the Bernoulli likelihood is mu to the power of x, 1 minus mu to the power of 1 minus x. Right? X now is 1. So this likelihood essentially is mu. So you can see that the likelihood function in terms of mu is just a linear function. So now you just merge them together, you calculate posterior distribution, it will end up with another data distribution. Okay? But of course, your parameters are changed. That's very natural because you integrate some information from the data, right? From the likelihood. Okay, so we can extend it to the categorical variable case, right? You have multiple categories, right? Rather than just the binary variables, right? Then it is very easy to see that Dirichlet prior is conjugate to the categorical likelihoods, and this is the Dirichlet prior, and this is the likelihood for any categorical observation X. Remember, X is a one-hot encoding, right? So if you multiply them together, you see that this form is just the product of each mu k to the power of this guy. This is kind of similar to the prior form, except that the power is changed. That implies the posterior distribution is also a Dirichlet distribution, right? But of course, the parameters change. You have to add the prior parameters alpha to the observed one-hot encoding X. I will leave this as an exercise for you. Again, I highly encourage you guys to derive this by yourself. X? X is an observation. Now, X, remember when we talk about categorical variable, right? We use one-hot encoding to represent the category, right? If you have 3 category, right? Your X could be 1, 0, 0, right? Or could be 0, 1, 0, right? That's our representation. That's why you can add X and alpha because they have the same dimension. They're just they're both k-dimensional vectors. Okay. Again, gamma prior is conjugate to the Gaussian likelihood in the sense that if you model your Gaussian distribution with mean mu and the inverse verse lambda. Right? If you assign this lambda a gamma prior, then when you calculate the posterior distribution, that means you multiply the prior and the likelihood here, you will end up with another gamma distribution, which is a posterior. And again, your posterior distribution has different parameters. Well, you see it's here, right? Again, check it by yourself. And we can extend it to the multivariate Gaussian case, where we can see that the Vcharge prior is conjugate to the multivariate Gaussian likelihood. Okay? So again, we are talking about the prior over the precision matrix. Right? So you assign prior over the precision matrix with this Vcharge prior, and then given this precision matrix, you got a likelihood of your observation X, which follows a Gaussian distribution if you multiply them together, and you will end up with another Vcharge distribution, which is a posterior. That's a very good question. If you don't have a conjugate prior, you cannot get, usually, I mean, in most of the cases, you won't be able to get a closed form posterior distribution. And in that case, you have to seek for other approximate inference method, like Markov chain, Monte Carlo sampling, or variational approximations, or message passing. We're talking about the easiest case where assume, okay, we're so lucky that our likelihood has a nice prior, and then you can very easily compute the posterior distribution with a closed form.
Why should we assume that the computer is solving the conjugate distribution? Just because it makes our computation easy?
Yes. Yes. Yeah, that's a very good question. Yeah, the conjugate prior is solely for computational convenience. That's also why it has many criticisms. We will get to the point in a minute. But anyway, just this example, like if you assign a Vcharge prior over the precision matrix of your multivariate Gaussian, you can obtain that your posterior distribution is another Vcharge prior. Of course, you need to change the parameters accordingly. Okay, so now we come to the point. Why should we use conjugate prior? So what's the benefit of conjugate prior? And unfortunately, there's nothing else except the computational benefit. Okay? That's why there are always criticisms about conjugate priors, right? People question that they're constructed just for computational convenience, but are they really appropriate? Okay. From modern perspective, do we really believe a gamma prior is the right prior for your inverse variance, or Vcharge prior is the right prior? So there's another problem, right? If you choose other priors which you believe from a modern perspective is more natural or more powerful or more expressive, whatever reason, right? They are usually more difficult to compute the posterior distribution. It's kind of like that dilemma. Like you want to enjoy computational efficiency or computational easiness, you have to restrict your prior form, right? You don't have other better reasons, right? But if you want to be more flexible, you want your model to be more reasonable, right? Then you need to seek a way to address the computational challenges. But anyway, this is just the one set of choices of building your prior and likelihood. Conjugate prior is kind of convenient in practice, and in many practical cases, even if you just assign a conjugate prior, it works pretty well. Right? But that does not necessarily mean we should always use conjugate prior. Okay. Any questions so far? Again, I highly suggest everyone to, manually check why they are conjugate, right? What's the posterior form? We won't be able to show you in the class, but it's not hard. Right? Okay, now let us talk about another very important concept. It's called exponential family. It actually plays the key role in approximate inference in modern probability learning. Right? So what is the exponential family? Right? As the name suggested, it just means a collection or a family of distributions. Right? They kind of share the same general form. It plays the central role in the approximate Bayesian inference. So what's the general form of the exponential family? You can view like, okay, this is my random variable x, and this eta indicates its parameters. So you can view like this distribution is parameterized by eta. Right? So the form is as follows. Right? So first, we assume there is some non-negative function of x which has nothing to do with eta. So we assume this additional h of x just to ensure you got some finite integral over the support. And in most cases, you can simply take it to be constant 1. And then the most important part is actually in the exponential part. Right? If you look at the power, right? So it consists of two components. First, we will say there is a function of the random variable x, which we denote by u of x. So this u, you can see is bolded. That means in general, we can view it as a vector. Right? We got a vector random variable as the input, the output is also a vector. So we call u of x as a sufficient statistics. And then we're gonna do the dot product between the sufficient statistics with our parameter eta. Again, eta here in general, we should view as a vector. So we call eta as the natural parameters, which determine the distribution. Mm-hmm. Yes. Yes. Yeah. So basically, if you want to determine any distribution in the exponential family, what we need to do is to determine the expectation of the estimate of the expectation of the sufficient statistics. So, and then to ensure that, this guy, their integral to be 1, right? You have to introduce a normalizer. And of course, this normalizer is determined by the parameters eta, right? So because it is just the integral of your h of x and this exponential term. When you integrate out x, you end up with the normalizer, which is only dependent on eta, right? So that's why we write this normalizer as a function of eta. Sometimes you see the literature is called partition function. So again, I want to emphasize this is a function of eta. Okay. So this is the most general form of the exponential family, and later we'll see how it carries the commonly used distribution. Right. So in some scenarios, we feel like if we just write 1 over z, eta is kind of like inconvenient. So you want to put z eta inside this power of exponential. How do we do that? Of course, we can take a logarithm and then take the exp over it. So that means we can simplify our form of the exponential family in this way, right? So in the exponential term, we got this dot product between the sufficient statistics and eta, and subtracted by logarithm of z eta, right? So this is called a log z eta. Is called log normalizer, a log partition function. So now let us look at some example of exponential family, right? So for example, we can take a look at the Bernoulli distribution. Yeah, you have to make sure that this guy dx equals to 1. This is according to the definition, right? Your z eta is defined as in this way. Huh? Yeah. If you define z eta in this way, then you can see that if you do this integral, it will be 1, right? Yeah, in the next, we just want to move z eta to the power of exp. So what we can do, we can take a logarithm and then take exp, right? We just move this logarithm 1 over z eta into the power. It's just the minus log z eta. So let us look at how we how Bernoulli distribution can be viewed as a member of exponential family, right? So if you want to convert it to the exponential family form, you can take exp and you can take a logarithm and then take exp, right? And you got this in your power of the exponential, which is x logarithm mu plus 1 minus x logarithm 1 minus mu, right? So now you can just merge terms regarding x, which is x logarithm mu over 1 minus mu and plus this guy, right? Okay. You can, because this is constant to x, right? You can move it out of exp. You got your form, right? 1 minus mu e to the power of x logarithm 1 mu over 1 minus mu, right? So now we can check that this obeys the general form of the exponential family, right? So we got our sufficient statistics rightly x, right? Right being x, and your h of x is simply 1, and your natural parameters actually is a logarithm mu over 1 minus mu. Right? So, but of course, we know that this guy is actually 1 minus z eta. We want to represent z totally in terms of eta. So we can simply do some kind of transformation. We can solve mu in terms of eta and then plug it into here, and we can finally get our partition function or normalizer as 1 minus e to the power of eta. This is one case, right? Again, highly suggest you to repeat this after class, right? To have a sense how the exponential family represents all kinds of distributions. Right? A second case is called a multivariate Gaussian distribution, right? So this is a density of the multivariate Gaussian distribution. You can see that, okay, in general, we will like multivariate Gaussian distribution is parameterized by this mean and the covariance matrix, which we usually call them as the expectation parameters or mean parameters. And in a minute, we'll see that we can make some kind of transformation and we can re-represent this multivariate Gaussian distribution in terms of the exponential family form. And then in an exponential family form, you got natural parameters. And natural parameters and these expectation parameters, they're kind of mapping between them. Right? Let's see this, right? So again, we can do some manipulation of those exponential terms, right? We can expand this quadratic term, and we can move the constant term to x outside, right? They're all here. And then inside, then the remaining exponential term only contains x, right? So you can see that this is also pointed out in our last lecture, right? The exponential term regarding x only contains two possible terms. One is the quadratic term, xx transpose. The second is a linear term for x, right? So accordingly, you can define your sufficient statistics to have two components. The first component is just minus half xx transpose, right? Here, right? The second one is just x itself. And then correspondingly, you can define your natural parameters as sigma inverse and the sigma inverse mu, right? You might kind of feel uncomfortable because we put some matrix in the definition of statistics, right? But that actually doesn't matter because we can see that this is a trace form, right? So the trace form, you can view as kind of like general dot product. In general, like if you do the trace of two matrix A transpose B, it is equivalent to first vectorize these two matrices and then do the dot product. So that means you can view like this guy as a vectorized XX transpose and this guy as vectorized sigma inverse, and then their trace is just their inner product. Okay. Then plus X transpose the sigma inverse mu, of course, this is just another inner product. In this way, and of course, h of x is 1, and in this way, we actually turn our multivariate Gaussian distribution to the general form of the exponential family, right? And our z eta, of course, is 1 over this guy, right? 1 over this guy, which is, you just need to change the sign of the power, right? 2 pi sigma determined half e to the power half mu transpose sigma inverse mu, right? And of course, if you want to represent this normalizer purely in terms of eta, right? From our definition a minute ago, right? We know eta, the relationship between eta and mu and sigma, right? We can immediately rearrange this form and then plug in our eta value. So now we can represent the eta totally in terms of components in eta. But again, I highly suggest you guys to do it by yourself. It's not hard. It will take like 2 minutes, but it will definitely deepen your understanding. So by the way, I mean, any question regarding these examples? Okay, looks like it's pretty straightforward, right? So here we just give 2 typical examples. You see that the gamma distribution, the Vcharge distribution, the beta distribution, they all belong to exponential family, right? And the most significant characteristics of this exponential family is here. So I want to stress on this point. So if you have some general linear structure in an exponential form in your distribution, it corresponds to the exponential family. So it means that, okay, if I want to do some transformation of your random variable x, I get up some sufficient statistics, and then I do the inner product with the parameters. This product actually determines the distribution, and then it is exponential family.
Expected value of variance, value of in general for this easy to calculate.
Yeah, we'll show it. We'll show it in a minute. Yeah, very good point. Yeah, you're always pointing to something you want to discuss in a minute. That's good. Yeah. Okay. We can see the mapping between, in this multivariable Gaussian distribution case, right? We can see the mapping between the natural parameters and expectation parameters, right? So this is the natural parameters, and this is the expectation parameters or mean parameters. In some literature, you will see them as the canonical parameters, right? Why? Because people are used to use those parameters to describe your distribution, right? When we talk about Gaussian distribution, you always ask, what does it mean? What is covariance, right? But in a more general sense, they actually have another form of parameters to represent them, and there is a mapping between them. In our homework 1, you see you'll be encouraged to derive their relationship in some bonus question. So the second point I want to mention is that there is an insightful connection between the two types of parameters. One is the natural parameters. The other is the expectation parameters through the so-called feature information matrix. Okay? And this connection acts based on essence of mean field variation inference and a very popular stochastic variation inference. It's called stochastic natural gradient inference, which we're going to discuss later. Okay, so now let us look at some important property of the exponential family. So it's actually a very, very important component in an exponential family is this partition function, z eta. Right? Actually, from the partition function, you almost can get everything. Right? How can we see that? Right? If you take a logarithm of the partition function z, and then let us try to take the gradient of the log partition and see what can we get. So applying the chain rule, right? We take the gradient of the log partition. We're gonna first put z eta in the denominator, right? Z, and then apply the gradient over z eta, right? Is 1 over z eta times the gradient of z eta, right? And according to our definition, z eta is an integral of this h of x and exponential term, right? This is just to ensure your whole integral of this density is 1, right? And suppose we have our exponential family satisfy all kind of regular properties, meaning that you don't need to worry about if you take the gradient, if you switch the integral and the gradient, you don't need to worry about the validity of doing so. Right? That means you can move your gradient inside this integral. Right? If you take a gradient over here, right? If you satisfy some mild regularity conditions, which we can just omit right now, right? So you can take the gradient inside this integral, right? So because it is a gradient with respect to eta, right? H of x is constant to eta, right? It's nothing to do here, right? And then we take the gradient with respect to this exponential term, right? This exponential term, of course, according to the chain rule, we just duplicate this exponential term again, and then take the gradient with this linear term, which gives us u of x. Okay. So now we can see a very good thing is that you got this gradient here, right? And then remember in the denominator we have this z eta again. Okay. So if you move this z eta inside this integral, what is this guy? It's unclear. Let me just erase them. Yes, here, right? Let me remove this. Okay, so we got the gradient of z eta is this guy, right? And remember, we need to divide this gradient by z eta, right? So that means if we divide this guy by z eta, right? That means I got z eta here. Okay. Again, because this is integral with respect to x, right? That's nothing to do with eta, right? You can just z eta is kind of constant to x. You can just move this z eta inside, right? That means you can put integral here, right? So now, if you just look at this part, it is this, right? So actually, you get the density of x here, right? And then remember, don't forget the u of x here. Okay? And then you do the integral, right? So what is this? Yeah, expectation, right? So that's a very, very nice property. Right? So that means if you take the gradient of the log normalizer with respect to eta, you actually are computing the expectation of the sufficient statistics. That's very, very important property of the exponential family. Okay. So the gradient of the log normalizer is the expectation of the sufficient statistics. Right? So we'll review this property when we study the proximate inference, especially if we have time to discuss about message passing. Like in a more general sense, it's called expectation propagation. We'll always need to do some moment matching. That means you have to compute the expectation of the sufficient statistics. Then the easy way is to just derive the log normalizer and calculate the gradient log normalizer. And here we have a even nicer property, which is that if you take the gradient over the gradient of the log normalizer again, you end up with covariance matrix of your sufficient statistics. Okay. So if you take one gradient, you get expectation of ux. Okay. If you take this guy again, you will give the covariance of u of x. Yeah, and this is gonna be left as your exercise in homework 1. Okay, so now let us look at if we do maximal likelihood estimation for the exponential family, what kind of result can we get? Right? What kind of general result can we get? Right? Suppose we have n IID observations, so x1 to x big N, right? How to estimate natural parameters eta, right? Again, we can write down the joint likelihood, which is just the product of each individual likelihood here. Right? And we take logarithm, it just, you know, because z eta is multiplied for n times, right? So it's minus n logarithm z eta plus eta transpose, and you have to sum over the sufficient statistics across all the observations. Then you set the gradient of the log likelihood to be 0. You solve that, right? It's pretty straightforward, right? You just set this guy to be 0, right? So you can see that the gradient of log normalizer will equal to average of the sufficient statistics across all the observations, right? From the result, what we have just obtained, we know that the gradient of log normalizer is actually the expectation, the true mean of your sufficient statistics. So you can see that actually MLE for the exponential family tells you that I'm gonna use the empirical estimate of the mean or empirical mean to represent the true mean of that exponential family distribution. Right? It's a very elegant result. Right? So this is kind of empirical mean, right? Empirical mean. So this is this similar like, for example, if you toss a coin, right, for 100 times, I want to estimate the parameter. I want to estimate the chance you see the heads up, right? How can I do that? This probably might be 0.6 or 0.7. How can I do that using MLE? I threw the coin 100 times. I just count the ratio of the heads up. Okay? So it actually has the same meaning, but the result for MLE result for exponential family just tells us, okay, this intuitive way to estimate the parameters can be extended to the exponential family. Yes. The empirical mean. Oh, if you want to get the parameters of the exponential family, you still have to solve this. You still get eta, but this result just tells you get eta, but whatever eta you get, but it's still gonna tells you, okay, the expectation under the distribution parameterized by eta will be this guy. This is the same thing. Okay, so the last point regarding the exponential family is that we want to give some conjugate prior over the exponential family. So actually, this conjugate prior applies to all the previous cases we just discussed. Like you can see that all the prior cases like beta to Bernoulli, like gamma to Gaussian, they're just the specific form of this conjugate prior. Okay. So suppose our likelihood is an exponential family distribution, right? Follows this general form, and then its conjugate prior will have this general form. So they have to share something, right? They have to share z eta. In the prior about eta, you got some z eta to the power of this nu, and in the exponential term, I mean, this prior must have some exponential form as well. You got this eta transpose kappa. This is another parameters, right? These parameters are inside the conjugate prior, and you also multiply with this nu parameter. And to verify why this is a conjugate, right? So you can multiply this prior with the exponential family likelihood, and you see that it is multiply them together, right? You just merge the terms. It's pretty straightforward. You can see that, okay, it corresponds to z eta to the power of nu plus 1, e to the power of nu transpose nu kappa, right? Plus the sufficient statistics of the observation x. Okay? So it actually follows another instance of the conjugate prior with the parameters changed to this guy and this guy. So We can see that interestingly, right? So nu here is usually referred to as pseudo count. You can view like, oh, okay, before I observe anything, I can assume, okay, in my prior space, in my mind, there might have some number of data points, nu, right? And when they observe one actual data point, which follows the exponential family distribution, I'm gonna increase my pseudo count by 1. That's my posterior. I got nu plus 1. And then my parameter, another parameter, kappa, now is changed to kind of a linear combination of the old kappa and the sufficient statistics of the observation. So their coefficients are nu over nu plus 1 and 1 over nu plus 1. So it's a weighted sum of the sufficient statistics from the prior and observations. Again, I will highly suggest you to try to verify this manually to get a deeper understanding. And even better, if you can try to associate the beta Bernoulli pair and the gamma Gaussian pair, even Vcharge and Gaussian pair, multivariate Gaussian pair, to map them into these special instances, that would be even better. That will definitely deepen your understanding of this. Okay, so we have introduced these two very important concepts. We'll see them again in our follow-up lectures. So what you need to know is that what's the definition of conjugate priors? What's the motivation of conjugate priors, right? Motivation is simple. It's just for computational convenience. What are the conjugate priors to commonly use likelihoods? Right? You don't need to memorize the form of those priors, but you should know. What are they, right? Like beta distribution is conjugate to Bernoulli, gamma is conjugate to Gaussian, right? And the definition of the exponential family. Okay? How to turn the existing distribution into the standard form of the exponential family, and very important properties of the exponential family, and the general conjugate priors to the exponential family. Okay, let's stop here today and see you on Thursday.